Hey, AP Scholars! I wanted to just show you what was happening in our most recent lesson, so I was going to do this video for you to see what happened on Tuesday, September 22nd, if you were not here. Or if you were here and you want to see it again. There's a second video that's going to be for this. So this is the first video, it's what I taught already in class. The second video is going to be about what I didn't teach in class, and everybody needs to see the second video. So just some of you will need to see this one. If you've already seen all about how binary numbers represent images and stuff, then you can skip this one and go to the next one about compilers, interpreters, and Java. So this one we'll get started. Is we learned about converting binary numbers from into decimal numbers and hexadecimal numbers and back and forth. But understanding that binary numbers don't just represent numbers is a key concept in computers in general. You can represent just about all of human knowledge and human logic in binary numbers. It's pretty fantastic. So let's take a look and see. We're going to go through sort of different aspects of human knowledge and human expression, and we'll see how they can be binary numbers. So to start with, we're going to talk about text. Text is, the letters and numbers and such, that symbols that you use to write things down. And written language has been around for a long time, and we have encoded just about every written symbol ever used in human history in binary numbers. Take a look at, for example, the letter A, capital A specifically. There's also one for lowercase a. You can see that it's got a hexadecimal number, 00401, and B would be 00402. And that corresponds, of course, to a binary number, which could be stored in a computer to remember that this is A, this is B. And the entire work of Shakespeare or Harry Potter or whatever can be encoded into binary numbers. And it's not just the phonetic languages, every language. We can just scroll. All these websites, by the way, will be linked either in YouTube in the little doobly-doo at the bottom, or in Teams, or maybe both, I don't know. So you can visit this. But just to kind of scroll through, we kind of start with the European languages, and then as you get further out, we get into all sorts of other languages, Hindi, Punjabi, Tamil, Thai, and then traditional sort of languages from Ethiopia, you name it. And there's just so many symbols to see. It includes pictorial languages like Chinese, for example, which we'll eventually get there. So every single character in the Chinese language, which is vast, they all have a binary number attached to it. Even emojis, like this clock emoji, is apparently, I don't know, I can't quite, I guess 23F0 is the number for the alarm clock emoji. So even like happy face and every emoji you've ever used has a binary number. And it's really cool because the whole world has agreed. What, even Braille? Look, Braille. How do you even read Braille on a computer? I'm not too sure. Maybe they have a 3D interface, I don't know. But anyways, the whole planet, every country has agreed that these are the numbers for these symbols. And that's pretty spectacular. That means that we can represent all of written human expression in these numbers, in binary numbers. And then computers can record them and share them. So we can send text messages and emails and all sorts of different languages. Here we are in the Chinese characters now, I think. I honestly am not very good at Chinese writing. My children are learning it, but I don't know it too much. But just look how vast. We're just scrolling for days now. Just vast. We will never get, eventually we would get to the end of this list, but it's very long. So I'm going to move on to the next thing. I hope that makes sense. So this character here, I don't know what I picked up here. Classical form in good condition as a horse. Okay, cool. Its number is 4B901. So, that's how text is stored in a computer as a binary number. Its actual value as a number isn't what's important. It's that it indexes one of these symbols in this giant chart, and computers all agree what that symbol is. So that's written language. On to pictures. Yeah, images can be represented as binary numbers as well. So for example, this is a picture with discrete pixels. I don't particularly like this one I chose because it's hard to see where the pixels are. If you ignore the checkered background, we have sort of this blocky shape, and a square this big, for example, could have been 1 pixel. So they just have numbers to represent each color, and at this time Nintendo was using, I guess, 8-bit graphics, and I guess I should double check this. I could be wrong, but I feel like they weren't using the whole bit for the colors, but I could be wrong about that. So basically, 8-bit means 8 bits, eight zeros or ones, and an 8-digit number, a binary number. What's the biggest number you can make in an 8-digit binary number? 11111111. That's 255, and including 0, that gives you 256 possible colors if you encode them with binary. So they just said red is this number, green is this number. This weird olive color is another number. They just picked all a bunch of colors and assigned them numbers, and then the monitor knows what to do when it encounters this data, or at least when the processor gives it the command to recreate that color. So pixels are treated as data, just the color inside of the pixel, and then you could just sequentially list the numbers for red, 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 and then nothing, and then a bunch of nothing, and then more red, and then olive, and then whatever, orange, and so on, and just kind of go across. So it just becomes this long sequential number that just goes across the rows and down the columns to describe the colors of each pixel. Of course, it needs to know the width and height as well of the picture, so it knows when, what number is the end of one row and the beginning of the next row. And that's metadata, data about the data. So, what is the size of this image? And that's stored in the picture as well. And that's just numbers, so width and height and so on. Images sometimes store other kind of metadata. For example, JPEGs. If you take a picture with your cell phone, or no, phone is just the word I'm looking for. If your location services are turned on, it can actually record the location of where you took the picture in the picture, and then sleuths and stuff can use that information to figure out where you were when you took that picture, which is sometimes used for evil purposes as well. So all sorts of numbers are stored inside of pictures. Some of them are for the picture itself, like what color is this particular pixel, and some of it is metadata. So you can represent a Mario here as a binary number. I was going to show you sound next, but this is blocked. I go to click on it, and it says it's a high-risk website, so I don't think it is. This is actually, wanted to show you how you can represent sound. The idea of, sound is just vibration, but how do you turn an entire symphony orchestra of many instruments playing and an audience clapping into a single vibration, a single wave that a speaker can produce with a magnet vibrating at high speeds, some kind of membrane. And I was going to show you this cool thing about Fourier transformations, where you can take, you can create complex waveforms just by combining simpler waves, stacking a whole bunch of waves together. And this was a great example of how you do that and how that gets made. It's even interactive. You can try it out yourself. I'll link this on the on Teams or in the YouTube video so you can try it out yourself. And I think it's pretty fun to see. I know that computers can make sound because you're listening to me right now. So if you hear my voice, you can take it for granted that sound can be digitized. But I would have liked to show you a little bit more how. Anyways, we'll move on. If we have images and sound, clearly you can make a movie into binary numbers as well, because a movie is just sound with lots of pictures that are shown at a particular frame rate to create the sensation of movement and animation. So movies, that's taken care of. How about logic, human logic? So thinking about something like making decisions. So that can all be done with binary numbers as well. A fellow named George Boole, this is what he looks like, in the 1600s, formalized all the math for using binary numbers to recreate all of human logic. And there was no computers around in the 1600s. So he didn't really even know this was going to be necessarily used for the practical purposes. He had no idea that someone would use it to make bots in a video game, or control important systems in a car that drive things around. Like, he didn't know what a car was. Like, this was all just him trying to think of sort of universal mathematical ways to describe things. His contemporary Rene Descartes first invented the Cartesian coordinate system, the x and y axis, to turn physical space and your ability to describe physical space into numbers. So it was in the same spirit that he was thinking about, well, could I do the same with logic, human thinking? Could I turn that into numbers? And so the way he did it was he decided to use binary, zeros and ones. And here's some example. This is a truth table generator. So I'll show you what a truth table is. Let's take a very simple example. Here's a question that you could turn into binary math. So a question, it needs to be a true or false answer, or a yes or no answer. And here's my question. Can I go to the movies tonight? And let's say the criteria is it has to be a weekend, so you can't go out on weekdays, and you have to have your homework done. So those are the two different things that are going to factor into our decision making. And the question is, if it is a weekend and my homework is done, then I can go to the movies. So you can describe that with a logical expression. So we could have a variable like W to say whether it's a weekend or not. And we can have another variable H for homework to describe whether I'm done my homework. And then the relationship is an and, because I have to have both of those things done to go to the movies, right? So this and this must be in place. So let's make the truth table. Boom, here it is. I'll zoom in. So here's our truth table. So let's imagine that ones are true, or yes, and zeros are false, or no. So this is the question. Can I go to the movies? Here's whether it's a weekend or not. Here's whether it's I'm done my homework. So if it's not a weekend and you're not done your homework, do not think about going to the movies. Get your homework done, and wait till the weekend. Hey, but if it's a weekend, but you're not done your homework, forget it. No movies. How about if it's not a weekend, but you are done your homework? Ooh, sorry, no go. You gotta wait till the weekend. But then that magical day comes where it is the weekend and you are done your homework and you can go to the movies. Do you see how that works? That's the truth table. Now just for a minute, think about what operation is happening here. Like if I was to put a mathematical operator between these two numbers and an equal sign here to produce an equation, what operator could I put in each one of these slots to make this true? So the answer is multiplication. If you look at this, 0 times 0 is 0, 1 times 0 is 0, etc. And then 1 times 1 is 1. So an AND relationship can be represented with multiplying binary numbers together. There's another relationship, the OR relationship. So maybe you have less strict parents that'll let you go to the movies if it's a weekend or you're done your homework. So let's see that truth table. So this time it's an OR operation. So if it's not a weekend and you're not done your homework, you're not going to the movies. But any other combination of those, then you can go to the movies, right? So notice what operation is going on here. This one's a little bit tougher. I think it's pretty obvious for like this row and this row and this row, but then it doesn't seem to hold true with this. So the answer is addition. So 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and then you would think this is wrong because 1 plus 1 is not 1. But remember, we're talking about binary numbers. So 1 plus 1 isn't 2 in binary numbers. 1 plus 1 is 1, 0. And so for this truth table, you can simulate it with binary numbers as long as you take the leftmost digit of the operation. So when we add these together, we're going to make sure we take the leftmost digit. For these numbers, it doesn't matter because there's only one digit. But if there's more than one, you take the leftmost. And there you go. You've just represented this OR relationship with adding. And then there's one other relationship that is essential. That's the NOT relationship. So it's just like the opposite. So if A is true, then not A is false, and vice versa. If A is false, then not A is true. And that's just flipping it. That's a really simple one to do, taking the inverse of something, right? So it turns out, and George Boole sort of demonstrated this, that all of human logic can be broken down into and, or, and not statements. You could build more complex expressions with just those three building blocks. And like you can see some over here, NAND, NOR, and exclusive OR, and some other ones that are built up with the or, and not. And that can recreate all of human logic, which is pretty phenomenal. It all just turns into adding and multiplying. And guess what? Multiplying is just repeated adding. So all of human logic can be recreated with adding and binary numbers. That's pretty cool. Thanks, George Boole, taking care of us in the 1600s, and that math turned out to be pretty important. I don't know what his friends thought of him at the time, if they thought he was wasting his time with this or what, but the world has been changed by his genius. Eventually, people started turning these, they took George Boole's ideas and they made mechanical computers. They thought this would be pretty interesting to create a machine that they would crank and it would have gears inside, and it could do operations with math and stuff, and possibly do logic as well. But they were too cumbersome. Like there's just so much you can do with a mechanical computer. But eventually this fellow comes along. This is Alan Turing. He's generally considered the father of computer science and computers in general. He publishes this paper over here. It's a little bit small. On computable numbers with an application to the Entscheidungsproblem. And basically in this paper, he demonstrates that any number is computable if you had a powerful enough computational device. Maybe not any number, that's actually not correct, but there's a vast amount of numbers in the world that you could calculate. You can't calculate like a repeating decimal, and you can't calculate an irrational number. You can estimate them, but because they go on forever, that's not possible within a finite machine. But everything else is computable. And so he proposes this idea of how would that work? How would that structure? And this is the theory that is required to build an electronic computer. And Alan Turing kind of proposes this idea. And this is in 1936. You can see the date here that he publishes this paper, which is the eve, just on the edge of the Second World War. And when the Second World War happens, his paper is suddenly a very important one, because all of a sudden a ton of math is needed to be done. Modern warfare requires math. And the problem he was asked to solve was the Enigma code. There's this legendary, unbreakable Nazi code that Nazi Germany used to communicate with all their troops, and it was basically unbreakable by human minds. It was just too complex, and it would even reset every day. So if you could break the code, it wasn't impossible to break it, but once you did break it, all that work was wasted, because at the end of the day it reset, and you just couldn't, humans just couldn't do it fast enough to break it regularly. I don't even know if they ever broke it even once during the day. But if they did, it was a waste of time, because obviously it resets. So then Alan Turing was asked to build this computing device he talks about, and of course it uses electricity instead of gears and stuff to represent the zeros and ones, and it can just operate phenomenally fast. And so he does successfully create this computer and breaks the Nazi code, and the Second World War ends up being won by the Allies, in large part, not entirely, but in large part due to the fact that the Allies knew what the Germans were talking about. The Germans thought they were talking secretly, but this electronic computer that Alan Turing created, using these concepts from George Boole and others, and his own research, demonstrates that you can do this. And he breaks the code, and the Allies go on to win the war, and Nazis were defeated. Yay! That's a good thing. So that's good. Later on, he goes on to publish this paper about this. I would read this one if I was going to read anyone. Computing Machinery and Intelligence. This is in 1950. This is a fantastic paper where he muses on the possibility of this being used to create intelligence. So this device that was designed for computation, you know, using George Boole's ideas about logic, he starts thinking about, could this machine actually think? And of course, artificial intelligence has come a long way since 1950, but it's Alan Turing that sort of understands where this technology is going, and makes this incredible prediction much early on, and sets out sort of ways to measure this. So it's pretty fantastic. I'll link this as well. This is a great paper to read. So that's good. He is a very important person. I don't know if I have the next picture ready. Oh yeah, here it is. So this isn't his computer, but once the Allies create that computer, gosh, I've forgotten the name of it. Bomb something. Oh, I forgot. Oh well, whatever. Anyways, the other computers are being made at the same time. The United States has a computer. They're using it to invent the nuclear bomb, to sort of do the math. It's incredibly complex math to figure out how to detonate a nuclear explosion. And then it just continues building from there. But computers at this time are enormous. Like this is they're inside. This man is inside the computer right now. It's just this enormous machine. And in part, it's so big because binary numbers are being sort of represented inside of these things called vacuum tubes, and it just takes up a whole lot of space. They're like, the size of a football, and to store 1, 0, and 1 in that size, like it's, if you want to have a fair bit of working memory to do these computations and to store reasonably large programs, well, you're going to need to have a lot of these footballs, and so these vacuum tubes. So it definitely doesn't scale well. This is the ENIAC we're looking inside of, which is a famous computer. So that invention, the vacuum tube, proves to be good enough for the time, but is definitely the bottleneck of this technology. It produces so much heat. They break down easily. They're expensive. They are big. They take a lot of power. So computers can't really go beyond this until someone invents the transistor. Transistors is a large transistor here. They are now microscopic, but this transistor is basically uses semiconductors to store the electrical current for a 0 and 1, and they also have the ability to take input and produce output as well. So transistors replace the vacuum tubes, and transistors just start getting smaller and smaller and smaller. I like this picture right here. It shows sort of like an old transistor, and then they're getting smaller and smaller, and now they're microscopic, to the point where on a single CPU, there's billions of transistors. And the CPUs are small, like the size of a postage stamp. Well, I don't know if you know what that means, but like the size of an icon on your phone kind of thing. Like they're minuscule. And so, it's pretty incredible. So transistors really paved the way for growth. The growth is so enormous that this fact is a great one. The entire computing power of the Allied forces at the end of World War II, with that computer that broke the unbreakable Nazi code, and the computer that like Einstein was using to figure out nuclear explosions, and basically these two things that changed the world entirely. That's the same amount of computing power as one of those birthday cards has that plays happy birthday when you open it. That's how far we've come, where we just throw away that power, that level of computing power. It's insane. There's something called Moore's Law. I should probably show you a graph of Moore's Law, where it basically says that the amount of computing power that we're capable of doing is doubles every 18 months, ever since the first computer was made. So every 18 months, computers get twice as strong. I guess the technical thing is the amount of transistors you can fit on a CPU doubles. And that's been true for the most part since, the dawn of computers. So we've come a long way in this. And it's all because of zeros and ones. It's pretty phenomenal. These transistors just make these truth tables a thing that can happen. So between data like language, images, sorry we didn't see this one, sound, which makes movies, and logic itself. And of course, there's also binary numbers that encode instructions as well, of like, which is what a program turns into. We have now so much computing power. So binary numbers have made all this stuff possible. And I guess the last thing I'm trying to remember the last thing I wanted to make clear was the connection with the transistor and the binary number is that you couldn't really store other bases very easily in anything. The beauty of the binary number and electrical storage is that it can either be the transistor can either have a charge or not have a charge. So it's either a 0 or a 1. If you tried to store like a decimal number in there, you'd have to have different amounts of charge for each digit. So like a 1 would be a little bit of charge, and a 5 would be more charge, and a 9 would be a lot of charge. But unfortunately, electricity doesn't stay stable that way. And I think people have tried to do this, and basically it ends up becoming chaos. Like numbers just start changing as, small fluctuations start happening. It's just really hard to keep those things stable. So that's where binary numbers make all that possible as well. In the actual hardware of these transistors, which simulate all the data and and truth tables and everything, that becomes a very workable physical device. It's basically just a switch that turns on and off. So on is a 1, off is a 0. So if you found this story interesting and you still feel like you're not, like we just dipped our toe in the water, so to speak, you're absolutely right. We barely even scratched the surface. And this is a very interesting story. So I recommend, if you want to find out more, this is a great book called Code by Charles Petzold. And you could dive deep into more details about how a computer is created and how binary numbers make this possible. He starts with something like Morse code and Braille and other codes that use zeros and ones, and he goes all the way to computers by the end. And by the time you finish reading this book, you have a really good understanding about why binary numbers are so important in computers. So that was a little bit of an intro to this topic, so to speak. I hope you enjoyed this, especially if you were away. I hope this helps the next video make sense. So tune into the second video where we're going to talk about how a program is turned into zeros and ones, and how Java, because that's the language we're studying, how Java is different than other programming languages in its approach to that process. Okay, thanks everybody. We'll see you soon.